Mathematically, why do I know that? I could write down the energy of the system, right? So the energy of that system is just, what is it, 1/2 mL theta dot squared, right? Plus mgl 1 minus cos maybe theta, right? And actually, if I look at that, because I have damping, I don't even have to do the numbers, you know, because it's got damping, I know that the energy is always going to be going down, right? So the energy is always going to be going down until the energy hits 0, and then it's going to stop at 0. So energy of 0 is going to be 0. So that implies that the energy is going to go to 0 just by looking at the energy, the time dynamics of the energy, and that actually is going to imply that theta is going to go to 0 too. Just by looking at the energy, the scalar function was easy to evaluate. Much simpler than solving the actual dynamics, right? And that's exactly the idea of the Lyapunov functions. All right. So oftentimes, if I can find some function, energy-like function, that has these kind of properties that is always going downhill, then I can make, and often those dynamics are much simpler than actually integrating the forward dynamics of the system. As long as it's going downhill, I can make long-term statements about it. This actually gives me more than convergence, right? Knowing this energy lets me know a few other things about the pendulum. It tells me about set invariance. Okay, so I can tell you some states. If you give me the initial conditions, I'll tell you some states that will never be visited, right? So if I tell you the initial conditions here with 0 velocity, you can tell me right away it's never going to go here, it's never going to go here, right? So the energy, it'll never go to a state where the energy is higher than the initial energy. Okay, and that's the idea. That's one way to talk about a set invariance of the dynamical system. Okay. All right. So in general, a Lyapunov function is just a scalar function. A scalar function v, which is some function of the state. We'll make it always greater than 0, except for the case where where x equals 0, we'll make it equal to 0. And if I can find a function like this, which is always going downhill, so where v dot of x is less than 0 until v dot of 0 equals 0, then that's going to be enough to show that x, some technical conditions that I'm just going to try to brush past here, that we're going to be able to show that x goes to the origin if we can write a function like that. That's the Lyapunov function idea. Okay, so I know most of you, or some of you know that very, very well, and I'm sorry if that was slow. But okay, so what I want to do today is use Lyapunov functions to analyze local stability of nonlinear systems, and I'm going to write programs that do this Lyapunov analysis for me. Okay, so let me do one more example just so you appreciate the computations that are about to happen in MATLAB. So let me just think of another dynamical system that we can analyze. So if I write down one of the simplest dynamical systems that's nonlinear, I'll do x dot equals negative x plus x cubed. If I can, that's a polynomial.